Hi, my name's Nick, and I'm going to talk to you guys a little bit about binary search trees today. So what is a binary search tree? A binary search tree is a data structure similar to that of the normal trees that we've been working with in past lectures, except we add a few special conditions to the tree to make it a little more efficient than other data structures when it comes to search, insert, and access. So what those special conditions are one, we see that each node has at most two children. 2, each node has at most one parent. 3, the values of every node to the right of a specific node are greater than the value of that node. And last, the values to the left of any specific node are less than the value of that node. So that could get a little confusing. I'll explain that more here with a picture. We see this is what conceptually a basic binary search tree may look like. We have a root node and we have its children coming off. You notice you have most 2 children and most 1 parent. And we see that for any specific node, all the values to the right are greater than the value in that node, and all the values to the left are less than the value of that node. For example, 10 right here, we have 15, 13, 16, and 21 are to the right. Those are all greater than 10. And we have 5, 6, and 8 to the left. Those are all less than 10. And that'll be true for any specific node in the graph, not just the root. For example, 15. 13 is less than 15. 16 and 21 are greater than 15. So this is a valid binary search tree. And we can see that this actually makes the search, insert, and access time log n by running through a simple example. If we are searching for the value 13, we simply start at 10. We evaluate if is 13 greater than 10? Yes, it is. So we'll go to the right. Is 13 greater than 15? No, it's not. Is 13 less than 15? Yes, it is. We'll go to the left. Is 13 greater than 13? No. Is 13 less than 13? Obviously no. So 13 must be equal to our value here. We found it in our graph. So that is log n search time. And what you'll see is that this is very good in practice because normally we have randomized data. So our trees will be somewhat similar to this, where they pretty even, spanned out like this. But if we get data that's, for one reason or not, in order where we have our smallest value at the root and all other values down to the right of it, like a long stick of values, then yeah, you'll see that in worst case, our search, access, insert is going to be O of n, because we have to linearly search through all of those by keep going to the right, to the right, to the right until we reach our spot. But because of, again, that we mostly work with randomized data, we're going to see that in the average case, we're going to get log n access time. So now I'm going to shift our focus a little bit to the actual code behind a binary search tree. So what we see right here is that every binary search tree is composed of a bunch of different nodes, and those nodes are basically just containers in the tree. So this would be an example of a node. And then inside that node we have a value. So right here, 10 would be our example of our value. And the reason I didn't write int, I wrote type, is because we can put any type of value in a binary search tree as long as we have some way to evaluate whether another value is greater than it or less than it. So we can use strings, for example, or any type of data structure we want, as long as we just have some way to evaluate it. Next, we have the children pointers, so left and right. Those are represented here by these 2 lines, and for each one you can see that. And then, lastly, we just have a pretty simple constructor to just easily be able to make nodes just by entering a value that we want to make. So then, right here we can see the actual code for our search algorithm. We can kind of see why it's so efficient. First of all, we see it's very simple to write, 10 lines of code max. And that's because we're able to recursively go through the binary search tree. We start with a simple base case of if our node that we're currently at is a null pointer, we know that our value isn't in the tree because let's say we were searching for 17. We'd go to the right, we'd go to the right, we'd go to the left, we'd go to the right. Oh, there's nothing here, we're at a null pointer. It must not be in the graph. So we return a null pointer. Then we look at if the value in our graph is less than the value we're searching for. So again, I'll run through this 17 example. 17 is 10 less than 17? Yes, it is. So we would recursively run our search in this part of the graph, right? And then lastly, if the value is not less than and it's not greater than, then in our last else case is just going to be, we know we've reached that value, so we're just going to return that node. So that's just a basic overview of the code and the structure behind a binary search tree. Hopefully I'll be able to talk to you guys a little bit more about it in a future lecture.